Welcome, everyone, and welcome to the next episode of Bird Math. Today, we're going to be talking about vertical asymptotes. What are they? How do you find them? What do they look like? Etc. And this is a very classic subject that is expanded upon in any Calculus 1 class of any college in the United States. So, if you're taking calculus now, this will be a great refresher or supplement to your course. Also, if you're just learning calculus for fun, this is also great. And let's get into it. So, you'll notice here that we have two functions, g of x and f of x. And our goal is to find any possible vertical asymptotes for g or f. And by the way, a vertical asymptote looks something like this. Where the function gets infinitely closer and closer to some, in this case, some value, in this case, x equals c, but it never actually reaches it. So that's what a vertical asymptote looks like. Now, the formal definition of a vertical asymptote is the limit of some function f of x as x approaches c equals plus or minus infinity. If this is true, then f of x has a vertical asymptote at x equal c. And that's the general theorem that we're going to apply here. So for most functions, the only exception I could think of offhand would be a piecewise function. For most functions, if a function is going to have a vertical asymptote at some x value, then that x value cannot be in the domain of the function. Let me say that again. If a function has a vertical asymptote, and it's not a piecewise function, the x value of where that vertical asymptote exists is not in the domain of the function. In other words, f of x, the function, is undefined at that point, which makes sense. When you look at a vertical asymptote, the function's always approaching it, but never actually getting there because it's not defined. So the first step of the way I like to solve these problems for any function is to find the domain. So let's start with g of x. We want to find all possible vertical asymptotes at g of x. And the first thing I'm going to do is find the domain of g. And hopefully you can see, without doing any math, just purely in your head, that the domain of g is the set negative infinity to 4 union 4 to infinity. And I'll have another video on how to find domains, but for right now, just go with that. So, in other words, the domain is all real numbers with the exception of x equals 4. So, that is a necessary but not sufficient condition for x equals 4 being a vertical asymptote. So, as of right now, x equals 4 is a possible vertical asymptote, but we don't know for sure yet. It's a candidate vertical asymptote. To find out for sure, we're going to take the limit. And we'll take the limit of g of x, which is x squared plus 8x plus 16 over the quantity x minus 4 as x approaches 4. And I like to do it, this is the two-sided limit, so we'll do it from each side. Because the behavior of a vertical asymptote, or the function as it approaches a vertical asymptote, can be different depending on the side that it is approaching from. So we'll take it from the right and we'll take it from the left. And you'll notice here, let's start with this right-handed limit. As x approaches 4 from the right, if we do direct substitution, which is how you should always try to solve your limits as your first step, try to just plug in whatever we see here for x. We plug in 4 here, we get some positive value up top, but we get 0 in the denominator. So it's undefined. So that's not good enough. We got to try another technique to solve this limit. And if you know your limits, which if you don't, that's okay, try to follow along. For now, I'm going to be posting lots of videos about how to solve limits within the next week or two. If you'll see here, this limit, the next technique I like to do is try to factor. So let's try to factor. And I see this numerator can certainly be factored into x plus 4, x plus 4. Okay. Now, hopefully you see we can cancel one of these, and we're left with the limit as x approaches 4 from the right of x plus 4. And now, with direct substitution, we realize that this is going to be 8. So, and a similar argument, pretty much the exact same steps, you also find that the left side limit is also 8. So what this tells me is the following. First of all, g of 4 is undefined. But x equals 4 is not a vertical asymptote, because the limits as we approach 4 from the right and left are not infinity or negative infinity. There's some finite value. So this tells me that this is x equals 4 is a whole in the function. And we know that for sure because we're able to cancel out that 4 in the denominator. That's a good way to tell. If you have some number undefined for a function that's able to be canceled out, it's usually not an asymptote, it's a whole. So, okay, x equals 4 is not a vertical asymptote for g. That was the only possible place a vertical asymptote could have existed because it's the only number that the function is not defined for, and therefore we can say g of x has no vertical asymptotes. Cool. Now let's look at that other function. I'll rewrite it down here. It was f of x equals x squared minus 4 over x. And just like before, we want to find all possible vertical asymptotes of this function f. So the first step, like before, let's find the domain. And just like before, hopefully you can do this in your head, you would see that the domain is all real numbers except 0, x equals 0. So f is defined for all real numbers except x equals 0. And so therefore, if f of x has any vertical asymptotes at all, it has to exist at the point x equals 0. Is a possible vertical asymptote. Now we don't know for sure yet, and to find out for sure, we're going to do the same technique and take the limit of f of x of the function as x approaches that possible vertical asymptote. So in this case, it's 0, and we'll do it from the right, and we'll do it from the left. So let's do the limit as x approaches 0 from the right first. When we do a direct substitution, we notice we get some negative value over 0. So that's not going to work. We cannot factor anything. I could factor the numerator into x plus 2, x minus 2, but that's not, nothing's going to cancel. It's not going to help us. But if you want, we can do that. But there's nothing to cancel. So this is one of those limits, and this is, by the way, called an infinite limit, where you have to slow down. There's no really mechanical way to solve this, and a lot of times in algebra, you can solve problems mechanically without really thinking. Add 5 to both sides, divide both sides by 2, x equals da da da. And you don't have to think much. Well, in this case, unfortunately, these types of limits, you do have to think a little bit. So when we're approaching 0 from the right, here's 0. We're getting closer and closer to 0, never actually getting there, but our x is getting closer and closer to 0. We're going to be taking numbers like 0.1, 0.01, 0.001, and we'll get closer and closer and closer to 0 from the right. That's what we're going to be taking for x. When we do that, it looks like we're going to be getting -4 up top, and the bottom looks like we're going to be putting very, very small positive numbers. And I like to write it as basically 0, but small positive infinitesimal numbers like 0.01, 0.001, 0.00001, while the top, that -4, is staying a constant. What happens when you divide a negative constant? Divide it by very small positive numbers like such. Well, 4 divided by 0.1, 40. 0.01, 400. By 0.001, 4,000. 40,000. It's getting larger and larger and larger. And I'm really sorry. This should be -40, -400, -400,000, because this -4 is negative in the numerator. So we have very, very small positive numbers, very close to 0, approaching 0 from the right, being divided into a -4. So the whole thing seems to be becoming very large negative numbers, and it basically increases without bound in the negative direction. And so the limit of x squared minus 4 over x as x approaches 0 from the right is -infinity. We're going to do a similar thought process, but we're going to be approaching 0 now from the left. So what kinds of numbers are we going to be taking? Well, we're going to be taking x's like -0.001, -0.001, -0.001, and so on. Very, very small, slightly negative zeros. So, and the top, by the way, as we do that, remains negative. 0 squared minus 4. It's going to be some negative constant up top, and very, very small negative numbers like -0.1, -0.01, and so on. When we divide these small negatives into -4, the whole thing increases in the positive direction without bound. Hopefully you see that this is positive infinity. And so I can now state that f of x at the point x equals 0 has a vertical asymptote. As we approach 0 from the right, we're going in the negative direction. As we approach 0 from the left, we're going in the positive direction. And it's going to look something like that, where 0, x equals 0 is undefined, and it's a vertical asymptote. And notice, for g of x also had a point, x equals 4, where it was undefined. But the limits were not positive and negative infinity. And in fact, that 4 canceled out the denominator. That's why it's a whole, as opposed to f did not cancel. And the limits, as we approach that number not in the domain 0, gives us infinity or negative infinity. In this case, negative infinity from the right, positive infinity from the left. And so f of x has a vertical asymptote at x equal 0. And because f of x only had one number where it's undefined for, which was that 0, that 0 is the only vertical asymptote. There's none other. Because in order for a function to have a vertical asymptote, it has to be undefined at that vertical asymptote. That x value cannot be in the domain of the function. Okay. And that's about going to do it for this video. I hope that made sense. I hope that helped you. I hope you guys enjoy this. We're going to be making a lot more videos here on Bird Math. If you like what I'm doing, please subscribe, like my videos, and please don't be afraid to suggest any topics or problems that you're having, whether you're in high school or college calculus. Please post them. I'll be sure to answer them, and I'll make a video about it. And appreciate you guys watching. Goodbye.